Welcome to Module 3. Module 3 is a discussion on the risk and reliability related to pavement design using the PMED design software. The same information or application is also appropriate or applicable to other mechanistic empirical-based design procedures, but the calculation of design reliability that we will discuss is specific to the PMED software. As a reminder, from Module 1 on the course schedule or roadmap, Module 3 will overview and discuss the risk and reliability for pavement design specific to and using the PMED design software. Reliability is discussed in Chapter 7 of the MEPDG Manual of Practice. Section 7.2 covers the concept of reliability in the PMED software and the design reliability for all pavement distresses predicted by the PMED software, while Section 7.3 covers the design reliability for smoothness and IRI. So let's take a moment and we will open the Manual of Practice to Chapter 7. And Section 7.1 is going to cover the recommended design performance criteria, which we will cover in the next module. But Section 7.2 is specific to reliability, the concept of reliability and how it's applied in the PMED software. Section 7.3 is basically the design reliability concept for smoothness itself. And you'll see some of the equations and the figures that are in the Manual of Practice that we'll use in the software itself, or in this presentation itself. So with that, we will go back to the presentation and continue. So within this Module 3, there are 3 learning outcomes. The first is to define and explain both risk and reliability as applied in the PMED design software. The second is to explain the reliability concept itself as specifically applied and used in the PMED software. The third learning outcome will be basically to illustrate the impact of reliability as examples on the predicted distresses and smoothness for pavement design. So now the definitions. What does risk mean? And what does specifically reliability mean? Risk is basically the occurrence of uncertain events which affect the outcome or the distresses that differs from the expected outcome. Risk is determined by the probability of the occurrence of a perceived threat and its magnitude of the impact on the outcome or its consequence. Reliability is basically defined as a pavement will perform its intended function for a specific period of time in a defined environment, that environment consisting of climate, traffic, foundation, and other site-specific factors without failure. And we'll define failure in just a minute. So risk is basically the occurrence of an unexplained or unexpected event, and reliability is related to the error or variance in the predicted distress value or performance measure. In other words, reliability can be quantified using the predicted and measured values, that come from calibration, while risk is much more difficult to quantify because it considers the occurrence of events that may not be necessarily included in the predicted values, especially related to calibration between the predicted and measured values. The MEPDG and PMED design software focus on reliability and not really the risk from unexpected events. With that, we'll turn to the definition of failure as applied in the PMED software to calculate reliability of a specific design strategy. So failure, what is failure? Basically, the failure is the condition of the pavement for which major rehabilitation is required. In other words, the condition of the pavement surface that can be measured and quantified that requires rehabilitation and or major repairs. Basically, failure defines the design criteria and or threshold values included in the PMED design guide itself. Failure also and or the design criteria or threshold values basically should come from how an agency operates and maintains its roadway facilities. The terms design criterion and threshold value are used interchangeably in the MEPDG documentation or manual of practice, but they basically have the same meaning. Reliability. The reliability equation shown here is the equation included in the manual of practice in section 7.2 that we just showed. The reliability is equal to the probability that the distress that's predicted will be less than the critical distress or threshold value, or basically failure criteria. The design criterion or threshold value will be discussed in greater detail in the next module, Module 4.1, that has to do with the inputs for the design criteria as well as design reliability. So remember, reliability is the probability that a pavement design will perform its intended function for a specific period of time in a defined environment without exceeding the critical distress level. Failure is an unacceptable condition and is defined as exceeding a distress value or level or threshold value. Risk is basically uncertainty. In other words, or stated conversely, uncertainty is the risk. And the risk is the possibility of the outcome not meeting the expectations of a design action and or design. So the risk is the quantification of uncertainty and the impact of the uncertainty on performance. If an event becomes a reality. As an example, there is a risk of overloaded trucks along a roadway segment or the occurrence of a 200-year-old cold temperature event or rainfall event that may not be taken into account during design. So the risk factor is composed of two groups or two risk factors. The probability one of those risk factors is the probability that an event will or will not occur, which is defined by reliability or can be defined through reliability. The consequence of that event, if it did or did not occur, is the second group of risk factors. Reliability is assessed by considering historical outcomes or behavior responses from the calibration in terms of measured and predicted values. Risk may or may not be directly related to those historical short-term outcomes that would be included in a calibration data set. Risk goes well beyond the concept of reliability. So, managing risk, or kind of further discussing risk and basically how they're managed within a design. So, our parameters, we have distress, performance, threshold values, reliability, consequences, and then the cost and or thickness of that risk and or the consequence. And so those are risk is usually managed as a function of the importance of the roadway itself or the roadway functional classification. In other words, the design threshold or performance threshold values typically become greater going from high volume interstate routes to much lower volume local routes. Conversely, reliability typically increases to reduce risk going from low volume local routes to high volume interstate routes, because the consequence of exceeding a threshold value typically increases, or the impact of the consequence increases going from a low volume local route to a high volume interstate route. In other words, interstate routes are more expensive to repair than local routes as a consequence. And stating that the cost and or the thickness, generally, as we all know, is going to increase going from low volume local routes to high volume interstate routes. So balancing the risk and the construction cost is always a concern of the designer. The more we want to have less risk, or we want to include less risk, higher reliabilities, that just means, or what that implies, or what the impact is higher construction cost, because the use of higher quality materials as well as thicker pavement layers. Now let's move to the reliability concept related to the hierarchical input levels. Even though we've already discussed these to some degree, or at least mentioned them in a previous module, we're going to go through the manual of practice, or show the manual of practice related to the hierarchical input levels as related to reliability. So the MEPDG hierarchical input level was introduced in Module 2. Section 4.2 of the MEPDG Manual of Practice provides the terminology and definition of the hierarchical input levels. The user should read this section on hierarchical input levels to understand the input levels and how they are applied in the Pavement ME software for pavement design to determine the reliability of a design strategy. So we're going to go ahead and open the manual of practice, and we'll go down to section or go up to section 4. Where the terminology and definitions of terms are provided. And under section 4.2, we see the hierarchical input levels. And we have input level 1, input level 2, and input level 3. And these are briefly defined in the manual of practice. And we're going to spend just a little time in the presentation on these input levels that are related to or have an impact on reliability itself. So going back to the presentation then. So the reliability and hierarchical input levels. The hierarchical input levels were included in the MEPDG basically for ease of implementation. When the payment ME procedure program was first introduced, there were a lot of variables, input variables, and concepts that many payment engineers didn't have a thorough understanding of, especially the input levels. And so the hierarchy input levels were established so that the initial agency's designers that didn't have access to some of the laboratory measured values for the engineering response and strength values directly, that they could be used or determined from, quote, best guess values for the input. So there's 3 levels. Input level 3 is the best guess value for the input. Input level 2 basically uses regression equations to estimate the direct input. And we'll go through these in a little bit more detail in just a minute. We will also, when we talk about each of the individual inputs for the different layers, the input levels, the material properties for each of the layers, we'll go through input levels 3, 2, and 1 when we talk about like asphalt concrete, Portland cement concrete, unbound base materials, and subgrade, as well as traffic, climate, and other input variables. So as we get into the discussion of the input variables, we're going to come back again to input levels 3, 2, and 1. This is just a introduction summary as related to reliability. So that's the input levels. So the hierarchy input level definitely has an impact on the error in most cases. Also, the best available data, it's important to remember, has been used basically in all global calibrations of the payment ME software. What best available data means for calibration is whatever data was available going from input level 1 was first used. If input level 1 was not available, then input level 2 was used in the calibration. And if input level 2 was unavailable, then input level 3 was used. So best available data was used in all global calibrations. So it is also a mix match between input levels 1, 2, and 3 in the global calibration. That's another item that's important to remember as we get into defining variability and the error between the measured and predicted distress values. And we'll get into that in just a minute. So the hierarchical input levels can have an impact on the residual error. And we have a graph that will graphically define residual error in just a minute. So if we did a calibration using only input level 3, that is best guessed values, so that will result in the highest error of the predicted distresses. In other words, the highest error between the predicted and measured distresses. Using input level 2 uses the regression equation to estimate an input variable. So we're getting more accurate, but we're still using regression equations to calculate or determine the input. So that error of the predicted distresses is basically called intermediate level or the mid level. If we actually measure the values in the laboratory or in the field to define the input variables, input level 1, we're measuring values to define the input, that's considered to have the lowest error of the predicted distresses or the difference between the predicted and measured distresses. Remember from the previous slide, however, the best available data for the input variables were used in determining the error or the residual error for most of the predicted distresses. So only one error term or definition is used to calculate design reliability. This means, in actuality, hierarchical input level has no numerical impact on the calculated reliability level through the PMED software, with the exception of a few of the pavement distresses like low temperature cracking or transverse cracking of asphalt pavements. And we'll get into that when we talk about flexible pavements in predicting the different distresses in the latter modules that are used for design. So, but since we use the best available data combining input levels 3, 2, and 1, hierarchical level was found to have very little impact because it's a combination of all three input levels for most of the distresses. And again, that may sound confusing now, and we'll come back to this concept as I noted when we talk about the individual pavement distresses and how the error was determined as used in pavement design. So again, best available data has been used in all global calibrations. Many local agencies or agencies that have done local calibration have also used best available data or a combination of hierarchical input levels. So, in summary, always use best available data or the input level that is consistent with the calibration process to minimize the residual errors and potential bias between predicted and measured values. With the above, hierarchical input level does not have a significant impact on the calculation of reliability for a specific road design strategy itself. Now let's get into the reliability concept specifically used in the PMED design software. So we're going to turn our attention to the concept of reliability itself. So the reliability concept, that is the risk the designer is taking when the expected result or the distress value is not being met. We want to make one additional comment that we'll come back to when we talk about the input levels or variables for the different materials, and also when we talk about the design strategies for both flexible and rigid pavements. Remember, the average value of the input variables is the input to the pavement ME design software. That is different from AASHTO 93, where in many cases, state highway agencies use a 90 percentile level for some of the inputs and not the average value. With pavement ME, remember, for a design segment, the average of all input levels is the value that is entered in the pavement ME design software. The input values of traffic, layer properties, foundation, and climate are just an estimate of the actual value, but the average values are used. So the greater the number of tests to estimate the input value to determine the average, the closer that estimate is or becomes to the actual or true value of the input variable. So the more tests you do, the better the estimate of the average across the board. And we know that practically everything varies associated with pavement design. Everything has variability. There's variability in traffic, materials, subgrade, climate, and other variables. Reliability, remember, is a quantification of the risk the user or designer is taking when the expected result or distress value exceeds the threshold value or design criteria, because the true value will differ and may exceed the threshold value or design criteria, because the true value differs from the estimated average value, or the true average value will differ from the estimated average value. In other words, the reliability is determined by considering the historical behavior, responses, and outcomes from calibration. So, traffic, layer properties, subgrade, and climate vary, but are assumed to have a normal distribution of the measured values. The average value for each input value is entered in the MEPDG software. The histograms or frequent and normalized distribution of these input variables shown on the screen are simply examples that the variability or the distribution of the measured values do vary for each of the different layers, and it's important to know how those variables do vary, so users can ensure they're making enough or sufficient number of measurements to adequately define the average value for each of the inputs. In addition, the measured performance indicator values, which is the outcome from the design, also varies, kind of as shown in this normalized distribution of measured performance values. The measured distress values used in calibration also represent the estimated average of the measured performance and or distress value that's actually there. So we have distributions in our input values, as well as we have a distribution or normal distribution of the outcome values or the measured distresses. So an important point that I've previously made is the average value estimated for each input variable is the input to the pavement ME design software for a design segment. So the user defines a design segment, and a user could have 1, 2, 3, or more design segments within a project. But once the design segments are set, then the average input values representing each segment is then determined. For traffic, the different layer properties, subgrade embankment properties, and so on. The same is true for the measurement of the performance indicators, and that's shown by this normalized distribution of measured values on this graph here. The average value is determined from observations of the pavement surface that were used in calibration. If different field technicians measured the distresses, the values will follow a normal distribution because each technician will not measure the exact outcome or distress on the pavement surface. There'll be differences in those measured distresses. But the values will follow, as well as just about all the input values will follow a normal distributions. And the average value is and was used in the global calibration process itself. Now, the reliability concept. This includes the variability from the distress measurements, the input variables, and the model error, basically of the transfer function from the calibration database. For pavement ME, variability is modeled separately and then coupled and then applied as an adjustment factor. The adjustment factor is simply the number of standard deviations of the residual error, to determine the reliability. Stated differently, a specific reliability defines the number of standard deviations from the mean residual error from the assumed normal distribution of the residual error itself. The mean value and the normal distribution, and if this is our threshold value, defined here, how many standard deviations of the residual error are we from the mean value of the residual error. So again, reliability simply defines the number of standard deviations of the residual error from the mean as the adjustment factor. To graphically illustrate that, the residual error, to start with, the residual error is the difference between the predicted and measured values using the average inputs. Again, it's important to remember we're using the average inputs. So we show a graph here of the observed distress value, whatever the distress is, versus the predicted value based on using average inputs. And this simply shows the line of equality from observed and comparing observed to a predicted value. So as we defined earlier in this module, the residual error is simply the difference between the predicted and measured value. So the difference between what we're predicting, the predicted value, and the value that we measured, or the measured value. So that's the difference between the residual error, simply the predicted value minus the measured value. The normal distribution, now shown to the right, is the distribution of the residual errors without any bias. So there can be a normal distribution of residual errors that do have bias, but hopefully after calibration, the bias will be removed, and so the average residual error is basically zero. So it's without bias. The important part here, though, is the residual error is the predicted minus the measured value. And we're using a distribution of those residual error for all these data points to see how that residual error varies to define the standard deviation of the residual errors. And that's what's used in the reliability concept. So, reliability starts with results from calibration of the transfer function to define the standard deviations of residual, i.e. without bias, as shown in this chart. So what's shown here, this is our predicted value, predicted distress value. This is the actual for an individual point, the residual error of the predicted minus the measured value, and it just shows those residual errors as a function of the predicted value itself. And this specific graph just shows the X's are for full depth pavement sections, the crosses are thick asphalt layers, and the open circles are thin asphalt layers, just showing the difference in the pavement structure, kind of as an example. So, standard deviations of the residual error can be a function of the predicted value. The standard deviation can also be independent of the predicted value for some of the distresses. So the key thing is to define, is the standard deviation of the residual error a function of the predicted value? Typically, the standard deviation will increase as the predicted values increase. In other words, the higher the predicted value of a distress, the standard deviation of those residual errors typically increase. But not always, but in general. So moving on, reliability and residual error. The standard deviation of the residual errors determines the reliability of a design strategy. So we've shown this normal distribution of residual errors in previous graphs. So the standard deviation of the residual errors is going to determine the reliability of a design strategy, kind of as we have previously explained. The hierarchical level comes into play now, where we can visually illustrate the difference between just using input level 3 versus just using input level 2 versus just using input level 1. So the hierarchical input level, however, can have an impact on the standard deviations of the residual errors. As an example, input level 3 represents our best guess values for the input level. So the standard deviations of the residual errors, if we just used input level 3, would typically be the highest or have the highest standard deviation of residuals. Input level 2, as a reminder, uses regression equations to estimate that input level. So we're trying to get a little bit more accurate, where an input to the regression equation was measured along the design segment. So we're trying to get more accurate. So theoretically, we would have a smaller standard deviation of the residual errors, kind of shown by this normal distribution of the residual errors. And if we used all input level 1, where we're measuring the input value along the design segment itself, this should be, the input level 1 should have the lowest standard deviation of the residual errors, because we're actually measuring it along the project site or along the design segment of a project site. So as the standard deviation of the residual errors decrease with input level, going from input level 3 to input level 2 to input level 1, the standard deviation of the residual errors should decrease. So the calculated reliability would increase for the same predicted value. And as we noted earlier, however, most global and or local calibration efforts were completed using best available data, which is a combination of the different input levels. So in that case, as we mentioned previously, the standard deviation of the residual errors may not be affected, or you may not see the difference of the standard deviation of the residual errors in your calibration data, simply because it's a combination of all three input levels. And as I previously noted, as the standard deviation of the residual errors decrease, input level 3 to input level 1, the reliability increases for the same predicted distresses. So what does that mean in terms of the graphical concept? So that's shown in this next slide. So remember the reliability equation from a previous slide in this module and from section 7.2 in the Manual of Practice. As shown in this slide, reliability equals the probability the predicted distress is less than our critical distress level, or our critical design criteria or threshold value, whichever term is used. But it's the predicted value will be less, the probability the predicted value is less than the critical distress value. So the probability is defined through the standard deviations of the residual. So this shows, as an example here, the distribution of the residual errors, in other words, standard deviation of the residual errors for between observed and predicted values. And so if we're at a 75% level, that means that 25% of the sections would have a higher predicted value than our observed value at this predicted distresses. And if we want a 95% level, or what the 95% reliability level means, is only 5% of our predicted values would be greater than our observed values. So once we know the standard deviation of the residuals from our plot of observed versus predicted values, we can then define, if we're at a 95% reliability level, that means there's only 5% of the predicted values greater than observed. 75% means 25% of our predicted values are greater than the observed value. And if we're at the mean, then 50% of our predicted values are greater than the observed value itself. So probability of our design is defined through the standard deviation of the residual errors itself. Again, illustrating that concept, but including both the normal distribution and the scatter plot between observed and predicted values. This slide illustrates the same concept, but includes the normal distribution of the residual errors, as shown by the normal distribution here. And to restate what was in the previous slide, the blue line basically represents the mean, or a 50% reliability. In other words, 50% of the predicted values are greater than the observed value, and 50% of the predicted values are less than the observed value. The red line shows the 75% reliability as in the previous graph. So in that case, 25% of the predicted values are greater than the observed value, and 75% of the predicted values are less than the observed value. The black line represents the 95% reliability, and all that means is that only 5% of the predicted values will be greater than the observed value, and 95% of those predicted values will be less than the observed value itself. So that basically is a graphical illustration of the reliability concept in payment ME. How that concept is applied, what you see in terms of the outcome from payment using the payment ME design software, will be illustrated in this slide itself. So this slide illustrates the computation of the predicted distresses at different reliability levels. The predicted distresses are basically going to increase with reliability level as illustrated here. So we know the standard deviation of the residual errors is a function or can be a function of the predicted values. Or it could be constant, but typically standard deviations of the residual is a function of the predicted value. In other words, standard deviation increases, or the standard deviation of the residual errors increase as the predicted value increases. And payment ME uses this concept of the number of data points or reliability, 50%, 75, 95%, and then it predicts those values, the predicted values at the different reliability levels as shown in the chart. So the blue diamonds shown here, that's the 50% reliability. The red boxes, that's the 75% reliability. And the black diamonds is the 95% reliability. So all the payment ME design software is doing, it's taking the standard deviations of the residual errors, and then it's calculating that value, the predicted value, using the mean inputs. Again, I'm going to make a reminder that this is all based on the assumption that the designer is using the mean input values for a specific design segment. Using those mean input levels, then the program will apply the standard deviation of the residuals and define what the predicted distress value is at using the standard deviation of the residual errors plus the mean of the predicted mean of the distresses from those mean input variables, as shown by the blue diamond. So, as shown, the predicted values increase with an increase in reliability through the software. And that's basically the payment ME concept. So, this is the graph mentioned in or provided in section 7.2 in the manual of practice. And basically this slide is a continuation of the application of the reliability concept in the payment ME design software. So basically the blue line is the IRI, predicted IRI, using the mean input values for all variables. So we're predicting IRI over time based on the mean input levels, and this is how it would increase at the 50% reliability. The program then applies a standard deviation of the residual errors, for the mean predicted IRI value. Mean predicted, and then the standard deviation of the residual errors around that mean. And that will then define the reliability. The blue dashed line is the IRI at the reliability level and used to define the acceptability of the design strategy. So this blue line here is the 95% reliability. So a user should always remember 5% of the observed value will be greater than the value predicted at a 95% reliability. Conversely, 95% of those predicted values will be less than the observed IRI reliability through the calibration data set itself. And again, one last reminder, the standard deviation of the residual errors can be dependent on the predicted value itself. Typically, the standard deviation of the residuals increase with the greater the predicted value based on the mean values themselves. So again, reliability is defined through the standard deviation of the residual errors using the mean input variables for the calibration sections. So with that now, let's move to some examples. And these next slides will simply be some examples illustrating the computation of the distress levels at different reliability levels through the PMED software. And this is simply to give the user or the individuals reviewing this workshop kind of a feel and indication of how the distress values increase with reliability over time. So this first graph displays the total rut depth calculated at different reliability levels. In other words, total rut depth versus age as predicted through PMED using the average input levels to determine reliability level. So higher reliability means a higher predicted total rut depth as shown here. And this red line is 50%, then we go to a 75% reliability, a 90% reliability, 95% reliability, and then the upper curve is a 99% reliability. So you can see reliability has a big impact related to the the average, the 50% reliability on the design, 50% versus 95%. 50% is less than 0.3, about 0.28. The 99% reliability, the predicted is about 0.48 inches total rutting. And then this shows the design criteria or threshold value that's entered into PMED and how that compares or is used to judge or determine the acceptability of a design at a specific reliability level. And as you can see for this section here, 90%, anything less than a 90% reliability will pass. Anything greater than about, let's say, a 92% reliability will not be acceptable for a 20-year design because the 0.4 inches rut depth will be exceeded within the 20-year design period for this example. Now let's move to transverse cracking. This is exactly the same as the previous slide for total rut depth, but in this case we have length of transverse cracks in feet per mile over time or age for over 20 years. And again, the red curve is the 50% reliability. The black curve here, or the dashed, is a 75% reliability. The solid black is a 90% reliability. Next line above that is a 95% reliability. And then the upper small dash curve is a 99% reliability. And again, the typical threshold criteria of about 1,500 feet per mile. And that shows the reliability values, which one are going to be acceptable and which ones will be unacceptable. And again, remember our previous discussion regarding consequences when a design is not met. So again, typically for very lower volume roadways, we have a lower reliability level. When we get to a higher volume roadway like interstates, we typically use a higher reliability because of the consequences of the predicted value exceeding our threshold value. So this is an example of top-down alligator fatigue cracking. In other words, top-down fatigue cracking, percent total lane area over time or age for a 20-year design. The same curves, 50, 75%, 90%, 95%, 99% reliability are shown in this example. And then a typical design criteria threshold value of 15% are shown. So it's just, we can look at these curves in different ways. We can look at when, at different reliabilities, when is the threshold value exceeded? And going from at a 99, that's about 11 years, and even at a 95% reliability, we don't exceed it over 20 years. Next one is bottom-up fatigue cracking. And again, same similar thing, 50% reliability, 75% reliability, 90% reliability, 95% reliability, and 99% reliability for bottom-up fatigue cracking. These examples also show typically how the distress develops over time for these flexible pavement distresses. And when we get into each distress type, we'll come back and show some of these, and this will be in modules, 5, 6, and 7. So the user or the person reviewing the workshop can get a feel of how distresses increase over time. And I'm going to go back just to show, starting with rut depth. Total rutting increases dramatically and then decreases over time. It increases, but at a decreasing rate. Transverse cracking can occur very abruptly. It can occur kind of uniformly, increase over time. So it kind of varies. Top-down cracking is kind of like rutting through pavement ME. It's going to increase, but at a decreasing rate, typically over time. And then bottom-up cracking increases at an increasing rate, typically more in terms of like an S-shaped curve over time for bottom-up fatigue cracking. So with that, now let's do a summary. We'll go through a summary of Module 3 that we've just covered on risk, reliability, and pavement design. So this is simply a summary of what we have previously presented. So basically, there's 6 key items. The first bullet point or first item, reliability, is determined or established based on the consequence of an event not meeting the threshold value, and reliability is specifically quantified through the standard deviation of the residual errors. Kind of for bullet 2, reliability of a design strategy is determined through the standard deviation of the residual errors. Also remember that for the standard deviations, basically of all the distress, those residual errors are assumed to have a normal distribution, as well as most of the input variables. Again, also remember the average values for the input should be used for a design segment. So bullet 3, the residual errors of the transferred function are defined through calibration. Another important comment for pavement design, use best available data. That would be consistent with the calibration process, especially the global calibration process, to define the standard deviation of the residuals. Some agencies have elected, as a side note, some agencies have elected to use their quasi-input level 1 for calibration, which is perfectly fine, but in that, and those residual errors are typically less. In other words, the standard deviation of the residual errors are typically less than where the standard deviation of the residual errors have been determined using best available data. So, but for all the global calibrations, best available data was used. So we need to be consistent with how the transfer functions were calibrated and use that input level for design, so we have a correct understanding and calculation of reliability. Hierarchical input levels or input level does not impact the calculated numerical reliability value when that best available data are used, because we're combining them for different sites. And then point 6, use the average value for the input variable of a design segment in accordance with the reliability concept used in the PMED software itself. So with that, that concludes Module 3, and the next segment will move to Module 4 and get into the inputs of the PMED software. And we'll talk about the inputs specifically for reliability, for the threshold values or design criteria, as well as the properties of the different layers, traffic, climate, asphalt concrete, the different layers, Portland cement concrete, and so on. So then that Module 4 will get into the specific input layer or input variable categories. With that, this concludes Module 3.